So here we go, section 7.3. Use functions involving e. Let me get my pen. So kind of a big day here. This e. E is not a variable. It represents a number. Let's just look right here. It's called the natural base. It occurs quite often. You'll see it, I think, probably more in science class than maybe math class, but pretty exciting. So there's only a few times that we represent a number with a letter, pi, or a symbol, I guess. Pi is also one of those. So pi represents 3.14. That's a good looking pi. Freehand there. But E represents the number 2.71828. It's an irrational number. I just keeps going. Kind of exciting. So something new for you. It is an irrational number where, and you've got this nice limit here that they define. I wouldn't, get worried about that. I'll never really require you to use the limit or exercise the limit, but it's nice to see where this comes from. And this, what happens is, as n gets bigger and bigger and bigger, this whole value approaches this constant here. It's kind of, makes you. I think most of us start with e and are a bit comfortable with it, and hopefully that will go away after working with it for a while. Again, remember that e represents a number. E is not a variable. Let me switch to the calculator for a second. So I did this for you on the calculator. The E button, let me show you, is right here, the ln. If you go second ln, then that's E, and you can raise it to whatever power you'd like. I raised it to the power 1, and then notice that is the value of 2.718, blah, 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 blah. Repeating. Notice here I can also get pretty close by from that formula and setting n to 100,000. And you should say, that's 100,000 is not close enough to infinity. But it's getting there, right? And you can see how close the numbers are. It's really in the fifth decimal place that I don't have the same accuracy. If I set n to 1,000,000, and 1,000,000's a lot of zeros, but that's still not even close to infinity, you can see how I've now gotten, the number to look almost exactly like e. But again, you should be saying, well, why don't you just plug e to the 1 in your calculator to approximate? But I just wanted you to feel how this limit works. So here we are on the second slide here. So we want to just work with e. E, again, you can take e to be just a constant. You can kind of play with it like it's x in here. So the rules for exponents, e to the 6 times e to the 3, we have the same base e. It would be, the exponents would add, which is, I'm excited as your teacher that we're reviewing exponents again. It's such an important thing. This is e to the 9th. If you wanted to approximate what this is, you could put it in your calculator, but we like it as we do like representing e quite often. Here it looks like we're dealing really with two problems. One is 18 divided by 2, which is just 9. And then when we have e to the 6th divided by e to the 4th, we see that we have the common base e, and we would subtract exponents. So that'd be e to the 2nd. I don't know what the second space is for. I'm moving on. Again, here's another rule with the parentheses, this power 2, that's power 2. You distribute it in. So here, I guess I'll use the 2 space. I'll say this is 4 squared, and then we're also dealing with e raised to the 3x. That's raised to the 2, and we multiply. When we raise an exponent to an exponent, we multiply those exponents. This should be 16 e to the 6x. I was a little worried that I wouldn't be able to show you neatly with my writing, so I rewrote it. Oh, they did the 6 minus 4. That's what they went. And here we go, example 2. So here you need your calculator, and this kind of writing is calculator notation. So can you take out your calculator? Maybe try this right now. E to the negative 2. I have to look at my answers because these numbers come out quite. Actually, I'm just going to show you what the answers are down below. I don't feel like writing, and I know my writing's not the most legible, but e to the negative 2, you should have gotten something like this on your calculator. No surprise, right? The negative would flip the 2.7. And then e to the 0.3 should also be a number less than 2.7, which is 1.3. So just nice to be able to So why don't you go ahead and try to do a few examples here. Maybe you just want to look at them. You don't have to write it down, but think about what we do with the powers for exponents. Again, great exponent review. Hit pause, and when you're ready, hit play, and I'll show you the answers. There you go. There are your answers, right? -3 plus 6 is 3. Here you should have squared 4, which is 16, divided by 8 is 2. Should have, when you raise e to the third to the power 2, that's e to the 6th, minus the exponents here, 6 minus 5 is e to the 1. And these would just plug them in your calculator. And here we go. So here's this function. Let's maybe put a box around it. This is still exponential functions, right? And why do I know that? Because the variable x is an exponent. So here it looks like these are all variables, but realize again, e is a constant. It's about 2.7. So you have some variable a constant 2.7 raised to some r value, which is typically a percentage. At least that's how it's given to you, x. And so what we'd like you to think about is that, hey, if a is greater than 0 and r is greater than 0, then this is going to be exponential growth. When r is less than 0, right, so like you could have e to the negative x, and we saw this today in class, this would actually make it 1 over e. So what I was saying is if you had e raised to the negative x, you really should think of that as 1 over e. That's what the negative exponent does, raised to the power x. And so you should think of that as like 1 over 2.7. And I keep just saying 2.7 because I don't feel like saying everything else. But you should think of that as a number less than 1, greater than 0. So we know this is exponential decay. So here we go, graphing. And let me start off by saying, I'd like to try to do these graphing, but I really need the calculator. So typically on assessments, I'll figure out a way to have you maybe match up some exponential. The key here is to look and start, and obviously, your eye should go to the e and realize you're dealing with the natural log. This is raised to a positive r value, so this will be exponential growth. The second example, because of this negative, it will be exponential decay. We're dealing with horizontal shift, vertical shift. Here we're not dealing with either. I'm a little, I like these examples. I'm glad we're seeing them. I think it's a little bit more than what I would like us to be able to do. Anyways, here we go. Let's go ahead and walk our. So we should plug in 0 for x. And when you raise e to the power 0, you get 1. Right? Anything raised to the power 0 is 1. And so you can see that 1 times 2 is 2. And that's easy. That's without a calculator. There's no way to get this number 3.64 without using a calculator. You would have to plug in your calculator 2e raised to the 0.6. So, just realize the calculator is given to you. Then you just plot these 2 points, exponential growth. Domain, all real numbers. Range, y is greater than 0. So for this guy, we would try to graph this without the horizontal and vertical shifts. So we would just raise, we would write e raised to the negative 0.35x. Substitute 0 in for x, get 1, and then substitute, 1 in for x and get this value here of 0.7. Both of the x values should be, subtract 1, and the y values we should subtract 2. Tricky problem. Again, be nice that you appreciate this is exponential decay in the same procedure, but to get this 0.7, you have to have a calculator. You have to plug in. We would, the domain here is all real numbers, and your range would be y greater than -2. For the sake, why don't you give this a shot? You're going to need your calculator when you set. So go ahead and give it your best shot. When you're ready to see the answers, go ahead and hit play. And there's your answer. So we started with this 0, 2. And again, you can calculate that without a calculator, but for the 1, 4, you'd need a calculator, and then they're just both shifted up by 3. All real numbers for domain, y greater than 3 for the range. So last equation for word problems, and here it is. This is the fourth and final equation for word problems. This is for continuously compounded interest. So continuous, we had been doing like we never did weekly. We did annually, quarterly, we did monthly. This is continuously. So every minute of every day, every second of every day, every millisecond of every day, you're compounding the interest. And this is the formula. P represents the principal or the initial amount, and R is the interest rate, which you would express as a decimal. So let's go ahead and see a word problem here. So you deposit $3,500 into an account that pays 4% interest compounded continuously. So when you read this, compounded continuously, you have to pick this formula. And so when we use the formula, we would put the principal at $3,500. Sorry if this video is getting chopped up. The software keeps crashing. I know my box now looks different because I had to reload it. Again, you're just putting the interest rate of 4% as 0.04, and we're solving for 1 year. Calculator comes out, plug in the values. Again, nice to look at this answer and say, yeah, that makes sense, right? 3,500, 1 year later, 4%. I wouldn't expect that much of an increase, and it's $142.84, which isn't bad. If you could try this problem on your own right now, right? So again, use that same formula. Here's your initial amount, there's your interest, but for 3 years. Make sure you change time to 3. Go ahead and hit pause, and when you're ready, the answer is coming right now. You should get this for an answer. Nice job.